Hi, everybody. Um, I'm Kevin Wolf. I'm the CEO and a co-founder of Wind Harvest. Today's topic is why would wind farms want vertical axis wind turbines? I realize I didn't include this in the slides, so I'm going to tell you a little bit of a history about this. Bob Thomas, he is one of the other co-founders of the company. He was the manager of the California Wind Program in 1980, and he started putting up, having the California Energy Commission put wind anemometer masts at 10 meters above the ground, about 30 feet, all over California to measure the wind resources. And he found them in what are now called the wind resource areas, small geographically tight little areas around the state. And I'll tell you a little bit more about them that later. But he realized there's a tremendously good resource near the ground in these areas. And he started a mission to figure out how to create a technology that could make use of this good wind resource near the ground. Um, and since then, a lot of additional science and information has come out about just how beneficial vertical axis turbines will be to wind farms. And that is the subject of this slide of this presentation today. So I'm going to go over here and present my deck to you and share that deck. And let's view it on the whole screen in a slideshow and continue to share. Okay, so this lovely graphic envisions our turbines in a single row, a little bit downwind of a row of horizontal axis turbines on the island of Maui. And these places in Maui and in places like California, there are small areas where it's intensely windy, and then the wind uh, dissipates and spreads out and is not nearly as strong. So here are these places. Can you get more wind out of them, energy out of them? And the answer is yes, you can. You can add vertical axis turbines to them. And there's all these other benefits that can come to the wind farm. And I will move on to that. But first, let's talk about this problem that's out there. Demand for energy, electricity is increasing. AI data centers, I don't like to talk about this, but air conditioning is going up all around the world as it gets hotter with global warming. For some reason, people want to increase their air conditioning, and that is an enormous load that is increasing almost everywhere. And then, of course, there's the EVs, there's heat pumps, there's the electrification of everything, a realization that the world is going to be electric and not burning fossil fuels has really hit the mainstream, and it's creating increasing demands for electricity. And of course, the supply is struggling to keep up. So the Trump administration has forcing coal plants that they're going to be shut down this year to stay open. There's really not a need to have those coal plants stay open, but that is what he's doing to meet this demand of AI, et cetera. The transmission lines, unfortunately, the Trump administration cut money for transmission lines. And of course, transmission lines are what's needed to move the electrons around and supply this electricity. So there's problems there. The best wind sites have been developed already. They're intensely windy in these areas, and then it gets more difficult to get to the uh, equally windy sites. And then solar takes a lot of land, which causes people to be hesitant about converting their property over to a solar facility. So that's a problem of supply. So what's the issue with horizontal axis turbines? Why can't they make use of this turbulent wind near the ground? And we'll talk about that a little bit, and I'll show you some pictures of it. But here's the basic concept. Near the ground, it's turbulent. Up high, it is nice, smooth, and laminar flow. And that is what the horizontal axis turbines need. And I'll go into some details about that in a little bit of why they need smooth flow. And other webinars we've done have talked about why vertical axis turbines, like our wind harvesters, can handle turbulent wind. But that's not the subject of today's talk. Um, I always like this slide as well. Oh my gosh, look at the wake that is coming downwind of these horizontal axis turbines right into the next one down. And so that reduces the amount of energy that the next horizontal axis turbine can achieve, and it causes turbulence problems for the next turbine downwind. So there are, how can this be solved? Well, future wind farms are trying to place these turbines further apart so they don't have these problems. Well, then that means they don't get as much energy per acre. And we'll talk about how vertical axis turbines can help with this. Um, I like this video because it gives you a sense of how many turbines can go onto a project. This is the Shiloh 2 wind farm in Solano County here in California near San Francisco. Rows of these vertical axis turbines are roughly 70 meters apart from each other. We have gaps in this vision of it because in case birds need to go around it. But our most recent kind of not really research, but talking to various ornithologists, is that birds will see the vertical axis turbines as a windrow along a farm field and from a distance and fly around them or over them. And we won't need to put gaps in between our turbines so that our vertical axis turbines can be even denser. Um, Another problem with wind. You know about offshore wind is being has a lot of problems, especially in places like California, where it gets to be a deep ocean right away, and you can't get the towers down to the base, so you have to float the turbines. That's a technology that they really haven't mastered yet. It takes a long time to develop it. Vertical axis, horizontal axis turbines, they last at the most 30 years. Well, maybe 40 if they got, from Denmark from a long time ago. But modern horizontal axis turbines are designed to not last much more than 20 years. And then places like California, they can't add any more turbines to the wind farms because there is a limit to how many horizontals can go before they start causing interference problems with their neighboring turbines. All right, so here's a big breakthrough. This guy, Dr. John DeBerry out of Caltech. I get a call from him, gosh, back in the 2000s, and he asked about the coupled vortex because Bob Thomas had published about it. We had gotten a breakthrough on placing two vertical axis turbines close together. We did that down in Palm Springs. There's another seminar about a webinar about that. And that showed that if you place these vertical axis, these H-type, straight bladed, not the Darius turbines, the kind of egg beater shaped ones, but the straight bladed ones, and you place them close together, you'll create these shed vortices, little whirlpools of wind downstream, and that creates conditions that are completely different than horizontal axis turbines, which send out a kind of a giant donut of a turbulent wind downwind. So he contacted us, checked out our turbines, and realized, oh, your turbines are too big. I need smaller ones. I need to be able to move them around. I need to do a bunch of experiments. So he got these Windspire vertical axis turbines. I think they're 1.5 kilowatts. And he put them in all kinds of different configurations. And over here on the right is, oh my gosh, he put so many sensors on it to collect data all over the place within this array. And that is the basis, that set of experiments that he did is the basis for a whole series of papers that have been written all around from Stanford to Cambridge, Oxford University to other places about vertical axis wind turbines and how they can change airflow. We also had Dr. Marius Paraschivu out of now it escapes me, university up in Canada. He took data that we got from the California Energy Commission grant about our coupled vortex effect. And he was also able to model out how these vertical axis turbines will shed wake and how long that wake will last. Now, here is a picture from a paper called by this set of the references here at the bottom. You can take a screenshot on it, but it's a great paper, and it basically says that, Yeah, if you put vertical axis turbines properly placed under horizontal axis turbines, you're going to see about a 10% increase in the energy output of the horizontals. Now, why? Because these shed vortices and this turbulence that comes off the back of the vertical axis turbines draw faster moving wind from higher altitudes down towards the ground. And it brings it into the rotors of the horizontal turbines. And the energy in the wind is the cube of the wind speed. So if you can increase that wind speed even a little bit into the rotors of the tall turbines, the cube law says, oh, it's going to get a significant increase in energy output. So that is the basis of the idea. Place these turbines upwind, draw down faster moving wind, and increase the energy output of the horizontal axis turbines. And of course, you're also making double use of the land. Now, I'm going to tell you a little bit about extending hot fatigue life by 10 years in another slide. So let's talk about this next part of the benefits of horizontal axis turbines. One is that the blades of horizontal turbines pitch, and they pitch to shed load. So, gosh, if they're straight like that and it's getting more and more windy, windier, boom, it creates gusts start to come. And a gust, as we talked about earlier, creates a significant problem for the horizontal axis turbine. So, what does a gust do? It causes the blade to shake. And what does the blade shake? It causes the drive shaft to shake. And I'll show you a picture of that in a minute. And if the drive shaft shakes, the bearings around the drive shaft wear out. And as you can see from this picture, oh my gosh, that is way up there. To take out the generator, you've got to take down the blades. Then you got to reach in, and sometimes you have to take down the blades. But you got to go all the way up there in a giant crane and haul out the drive shaft, bring it back down to the bottom, bring it back up and replace it. These cranes can cost $10,000 a day to rent and $50,000 to set up. So it becomes quite an expensive process. And therefore, the horizontal axis turbines have this problem. They want to keep the wind farm at 100% capacity. To do that, they need to keep their blades unpitched until they get to what's called rated power. Rated power is the wind speed at which the generator is maxed out. Once it gets maxed out, the blade pitches so it doesn't overstimulate or produce too much energy for the generator. If you pitch it early, you lose power. But if you keep it too long and a gust comes, then you got a repair problem. So modern wind farms, not all, but a lot of them are adding additional capacity. So if it's a 100 megawatt wind farm, they're adding another 10 megawatts so that all the turbines in the wind farm can pitch earlier. And some studies have shown that the horizontal axis turbines in these, if they can pitch earlier, they can last another 10 years. So instead of lasting only 20 years, they can last 30 years. So that's a huge benefit. Reduced repair cost, longer life of the turbines, and maintain full capacity of the wind farm. And I'll tell you a little bit more about that in the next slide. Let's talk about these horizontal axis turbines, what they look like. So you can see there's the three blades. You can see up here on the top there is a pitch mechanism. That blade pitches. There is a motor in there that causes that blade to pitch. And then it comes down a drive shaft to sometimes there's a gearbox, sometimes there's a direct drive. Gearboxes have to be maintained with fluid, just like in your car, you got to change your fluid, your transmission fluids, your motor fluids. Same with here. And so that creates a maintenance problem and a potential wear and tear problem. So that is and then they have this what's called a yaw mechanism. The turbine, a horizontal turbine, pitches into the wind. As the wind direction changes, the turbine pitches to increase and maintain the maximum amount of energy that they can. So Yaw mechanisms are motors. They have oil, lubricants. They need maintenance. They have parts that wear out. So this turbine is significantly more complicated than our simple vertical axis turbine. Drive shaft to a generator, a direct drive generator. We've got five lubricant cartridges, three on the drive shaft, two on the generator, and then we got a brake mechanism that we rarely use because this direct drive generator like ours is like an EV. You do electromagnetic braking. So that allows you to not have to have nearly the maintenance issues that horizontal axis turbines have. And the work is not done way up there at 200, 300 feet above the ground. It's done at 40, 50, 60 feet above the ground, which is a lot easier to get people to climb those ladders and go up that height. And it's simple repair work or maintenance work. Um, so that is a reason why you don't want the horizontal axis turbines to break down and the benefit of pitching blades early. Um, so now here is the use case that I'd like to show. You have a horizontal axis wind farm, which is all the wind farms there are in the world are all using horizontal axis turbines. That's called a 100 megawatt wind farm. You add in 25 megawatts of ours, but you don't change the substation and you don't add additional transmission lines. So up to about 20 miles per hour, and let's say the rated power of all the turbines is 25 miles an hour winds. At that point, all the turbines are running 100% capacity. But the horizontals would love to be able to pitch their blades at 20 miles an hour so that they don't have the gust hit them. Great. You have your extra 25 megawatts of vertical axis turbines. Horizontals, go ahead, pitch your blades. Verticals, keep generating. The wind farm stays at 100 megawatts all the time. The horizontals avoid the gusts. They have a longer life, they save repair costs. The transmission line is more fully utilized. When it's less than 25-mile-an-hour wind speeds, the whole wind farm is producing 25% more electricity from the vertical axis turbines. And the wind farm owners making more money because they're getting more electricity from their land. And most owners of the land get paid a percentage of the electricity generated. So if everything generates more electricity, then the landowner makes more money, the wind farm owner makes more money. It's just a win for everybody. I'm not going to say the win-win joke. No, okay, it's not a win-win. It is a win-win. Okay, let's leave that go. Okay, so what's another use case for why wind farm owners might see advantage of vertical axis turbines? In this case, it's like, well, put the AI data center right on the wind farm, keep the existing wind farm to produce the electricity under its contract to produce energy for the grid, but add that whole second layer and use that energy, maybe including some solar in between the rows, maybe including some storage, battery storage, and power the AI data center. Now, if it's allowed, the transmission line, when it's not windy or it's not sunny, the transmission line can bring the electricity that the AI data center needs. Or it can be off grid, and you can use the solar, wind, battery, and maybe a small gas generator as a backup. And now you can provide that AI generator with the AI data center with a very good source of reliable electricity without having to stand in line for the transmission queues, which are the ones that are really slowing the AI down. How do they get access to electricity? So that is one of the things that we hope to be telling you some good news about here in the next few weeks. I can't tell you about it quite yet because I don't have the letter of intent signed, but just to let you know that idea there is a winner of an idea, and we can lock in the 40 to 50% investment tax credits so that these projects have a 4-year build out and an opportunity to make this happen. But I'll tell you more about that in the next few weeks. Okay, so we're moving on. That's the AI data center option. This is where I wanted to kind of give you an example of where these vertical axis turbines could do really well. On our website, in our library, you can find this California Mid-Level Wind Resource Report. It is a report we sent to the California Energy Commission that shows that within the existing wind resource areas, they could go from 6,000 megawatts of horizontal axis turbines, and they could add 15,000 megawatts, 15 gigawatts of vertical axis turbines underneath the horizontal axis turbines. Now, I'm going to take a little note here. Why do I keep saying vertical axis turbines and not just wind harvesters? Because 15 gigawatts, 15,000 turbines, 15,000 megawatts at 14 turbines to the megawatt is over 200,000 turbines. That is a lot of machinery. It would be very difficult for any one company to supply all that. So Wind Harvest's strategy is we got the patents. We want Vestas and GE, Siemens, and the other companies to come on in. The market is big. Um, Come pay us a royalty fee, pay us for the license of the patents, and help build out this massive worldwide resource underneath the existing wind turbines. So I'm going to go show you that this red area, this is the San Gorgonio Pass. If you come from Los Angeles out to Palm Springs and you go through Highway 10, on the north side, up here is the San Gorgonio Mountain. On the south side is Mount San Jacinto. And in between, it funnels a massive amount of cold ocean air through a very narrow pass into a very hot desert. And that causes it to speed up. Now, what I'm going to show you next is the Alta Mesa Hills. Oh, so you've got it speeding up through the gap of these mountains, and then you accelerated it again over hills, and now you've got an even faster wind speed near the ground. This picture here on the left comes from the 1985 California Energy Commission Wind Atlas that kind of explains how wind speeds up over hills, and it speeds up at the end of the hill. When the wind drops behind the hill, there's another speed up effect. So I'm going to zoom in on this site and show you that, here is a close-up of that Alta Mesa Hills. I'll show you another version of it in just a minute, but we showed, well, how many vertical axis turbines could we add in here? And we could add in close to 100 megawatts. Now, these wind speeds are in meters per second. So when you see a 10 meter per second or a 9 meter per second, that's 18 to 20 plus miles an hour average annual wind speed. It is such a massive resource. This is one of the best resources in the entire world. And you're going to see that it is not utilized. The old turbines broke down over time and they have not been replaced. It sits there. Roads in place, even old foundations. You'll see this in just a second. It's ideal for us. And with that, I think I'm going to go over and share my screen. Stop share, and I have to do it again. Share again, and now I'm going to go over to the Google Earth, and now I'm in Google Earth. I really like Google Earth. It is an amazingly free tool. See, those are the hills. This is the Alta Mesa Hills. Down here is the flat between the mountains. And if I zoom back out, there is Mount San Gorgonio, and over here is Mount San Jacinto, and you can see how it squeezes in. And there are the hills. And the hills create an enormously impressive wind resource. So add in our vertical axis turbines. Oh, yes, I wanted to show you these dead horizontal axis turbines. Oh, look, here's one right here. Look at the shadow. Oh, where are the blades? Oh, there are no blades. This turbine has had its blades removed, I think for safety purposes, and so it's not even operating up here. This is sitting there waiting for somebody to come in. Now, what happens is A lot of people do not like the tall turbines on these sites because they can see them from a far distance. So there's opposition to the tall turbines. So now you could maybe you leave the tall turbines out and you just build it out with vertical axis turbines, put in 100 megawatts, and down here on the flat land, oh, look at all that nice flat land for a AI data center. So you wheel the energy down, and just like it's wheeled down already, and you supply the AI data center there. And oh, wow, it's so sunny down there that, of course, this is a lovely Palm Springs area. Look, there's solar farms in among the wind farms already. So you just go back up here and you add solar underneath it, and you add your AI data center down here. And if you need additional energy for that AI data center, because maybe you wanted to make it a hyperscaler and have hundreds of megawatts, well, then let's look at the Calabazon. Where does it go? Hang on a second. I think it's over here. There it is. Ah, there it is. So here is another roughly 100 megawatt site. And you can see the horizontal axis turbines are there. There they are. And how many rows of vertical axis turbines can you get in? And you could then add another source of electricity within an existing wind farm to supply that AI data center. So that's the big part of my story. Now let me go back to share one more time my lovely slideshow, and there I am. And okay, so just as a wrap up, vertical axis turbines draw faster moving wind into the horizontal axis turbines when they're set up correctly. It allows the horizontals to pitch early to avoid gusts of wind. It makes them last longer, and it reduces their repair costs. There is this synergy as well in wind farm maintenance. That crew that's out there is fixing up vertical axis turbines and horizontal axis turbines. There's always synergy when you have double the capacity per acre of land, less driving, all kinds of stuff. You get a double use of the infrastructure that's already been paid for, the roads, the land, the transmission line, and it reduces one of my other things, wearing my environmental hat. It reduces the amount of land that needs to be built out for solar and wind farms if you can use an existing wind farm and double or triple or quadruple the energy output. So that's one of the reasons why you should be investing in Wind Harvest, to help us bring this new technology to the world's wind farms and help out the world get a lot more renewable energy at a very good price, in part because, oh, these are the windiest places in the world. They produce a tremendous amount of energy, but they need more vertical axis turbines to make use of that resource. All right, well, thanks, and thanks for everybody who's already invested. Let me know. There's my emails all over the place. You can contact me, and I'm always glad to talk to folks. Thanks, everybody. Bye.